So today the topic is rectangular waveguide and different modes of propagation. Now to start the topic, let's have a look what is a waveguide. A waveguide is a rectangular or a hollow circular cylinder and perfectly conducting walls within the area or within the surface, and inside these perfectly conducting walls in which there is a hollow cylinder and waves are guided from one place to another via this hollow cylindrical type structure. Now, what are the waves that are used to conduct by the help of a waveguide? Actually, 3 to 300 gigahertz frequency of waves, they are propagating from one place to another by the use of this waveguide. And while we are talking about the different modes of propagation in a waveguide, we actually concentrate towards the electromagnetic theory to discuss these different modes of propagation inside a waveguide. So let's start this discussion. And this is a extensive mathematical discussion. So just be with us. Now, the Maxwell's equation for the region inside the waveguide, that is inside the hollow cylinder, as I have told that the surface of the waveguide, the external surface of the waveguide is actually a conducting metallic layer. But inside the waveguide there is a hollow cylindrical like structure and dielectrics are there inside the hollow structure. So the Maxwell's equations which are applicable for the region inside the waveguide will be curl of H that equals to epsilon 0 del E del T. Let it be equation number 1. Then curl of E that equals to minus of mu 0 into del H del T. Let it be equation number 2. Then divergence of E that equals to 0. Let it be equation 3. And then divergence of H equals to again 0, and it is equation number 4. So these are the Maxwell's equations which are applicable inside the hollow cylindrical like structure of the waveguide. Now the waves to be propagated be monochromatic with time dependence e to the power minus I omega t. So the equation number 1 and equation number 2, if the waves can be written as, let the magnetic field or magnetic field H can be written as H0 e to the power minus of I omega t, or E can be written as E0 e to the power minus of I omega t, e to the power minus of I omega t. Then what we can find that while curl of H or curl of H can be written as, equation number 1 can be written as curl of H that equals to epsilon 0 and then del T of E. So del T of E makes minus I omega E0 e to the power minus I omega t. That means minus I omega capital E. That will be the value of del E del T. So minus I omega and then capital of E. Let it be equation number 5. So curl of H becomes minus I epsilon 0 omega E. And what will be the value of equation 2, that is curl of E? So again, for the value of curl of E, as it is given as minus of mu 0 del T of H. So while taking the value of del T of H, it will be minus I omega H0 e to the power minus I omega t. That means minus I omega capital H. And here a minus already appears. So minus minus makes plus. So I omega mu 0 capital of H. I omega. So it will be I omega mu 0 capital of H. I think up to this you have no problem, right? So now let's move on to taking the value of curl H and curl of E. So let's find out the value of curl E first. Now curl of E. So just I'm wiping this out. 1, 2, 3 and 4, and then find out the value of curl of E at first. So curl E, what will be curl E? As we know that while taking the value of curl E, it will be I cap, J cap, K cap, then del X, del Y, del Z, and E means EX, EY, EZ. Okay? So it will be I cap del Y of EZ minus del Z of EY plus J cap del Z of EX minus del X of EZ plus K cap del X of EY minus del Y of EX. So this is the value of curl E. And now this curl E is equals to I omega mu 0 H. I omega mu 0 H. Now as we can find that curl of H, or rather we can find it more easily by, let's find out, let's take the curl of equation number 6. Taking curl of equation 6. So curl of curl E. So it will be curl of curl E. Then it will be I omega mu 0 curl of H. And we have the value of curl of H in equation 5. So let's put this value. That means I omega mu 0 and then minus of I omega epsilon 0 E. So it will be I square means minus plus, then omega square mu 0 epsilon 0 capital E. It will be the value in the right hand side. And now curl of curl E means we have curl of curl E means we have delta square E. A cross B cross C, we are using the vector identity of A cross B cross C. That means gradient, nabla, and then delta E minus of E, and then curl of delta cross delta. So it will be delta square E, and then it equals to omega square mu 0 epsilon 0 capital of E. So we can have, it will be negative, so we can have delta square E minus of this, and here a minus already present, so it will be plus omega square mu 0 epsilon 0 capital E, that equals to 0, or we can have delta square E plus omega square, and as we know that mu 0 epsilon 0 is nothing but, it can be written as C equals to 1 by root over of mu 0 epsilon 0. So mu 0 epsilon 0 is exactly equals to 1 by C square. So it will be omega square by C square, omega square by C square capital E equals to 0, or we can write delta square plus omega square by C square into capital of E equals to 0. So let it be equation number 7. So we have, by taking the curl of equation 6 and then substituting the value of equation number 5 in the right hand side of equation 6, we have the equation delta square plus omega square by C square into capital E equals to 0. And this is nothing but the wave equation in terms of capital E. As you can see that similarly, we can show that the magnetic field intensity or capital H also satisfies this wave equation, and for this to deduce, you have to take the curl of equation number 5 and then you have to substitute the value of equation number 6 into the right hand side of equation number 5, and then you will get the similar type of value, just delta square plus omega square by C square into capital of H equals to 0. So similar expressions can be deduced, can be derived, and both of the electric field as well as the magnetic field satisfies the wave equation given as derived in equation number 7. Is it okay up to this? Just give a thumbs up if it is okay, or you have any query, just ask me. Okay. So now we are interested in the solution that actually represents the waves propagating along the axis of the waveguide. Now the axis of the waveguide is taken as the z-axis. So now we are interested in the solution which can represent the wave equation or the waves which are actually propagating. Along the axis of the waveguide, and the axis we are taken it as the z-axis. So we actually get the solution of the form that is capital E, which is xyz t, capital E as a function of xyz and t, and it will be of the form E0 e to the power I kz minus omega t. So we are seeking solution of the form, and now this E0, actually this is the amplitude of the wave, and this amplitude part is nothing but it is a function of x and y. This E0 is actually a function of x and y, so you can write it as E0 xy. And again, for the magnetic field part, the similar equation is also applicable. So for the magnetic wave equation, you can write xyz t, again h0, which is similarly a function of x and y, and then e to the power I kz minus of omega t. So let these two equations be equation number 8. Okay, so we are seeking this type of solutions as we are considering the waves are propagating along the z-axis, and the z-axis is nothing but the axis of the waveguide. Now let's talk about again equation number 5, and now we are going to find out the components of equation number 5, that is curl of H. So let's find out. Now we have to find out the components. So curl of H, and that means I cap, j cap, k cap, del del x, del del y, del del z, then hx, hy, and hz, and this will be equals to minus of I epsilon 0 omega, and then E means Ex into I cap plus Ey into j cap plus Ez into k cap. Don't be confused with these two i's. This is the complex number and this is the unit vector along the x-axis, right? So now expanding this, we have I cap. Now del del y of hz minus of del del z of hy plus j cap del del z of hx minus del del x of hz plus k cap, and then del del x of hy minus of del del y of hx, and that equals to minus I epsilon 0 omega Ex into I cap minus I epsilon 0 omega Ey into j cap minus I epsilon 0 omega Ez into k cap. So I have expanded both the sides. Now comparing the components, I cap with the left hand side and the right hand side, j cap and then the k cap, we have three equations. So now I am going to remove this equation number 8 and writing the different components. First of all, the I cap components, it will be del del y of hz minus of del del z of hy, and then from the right hand side I have minus I epsilon 0 omega into Ex. Okay. Now the second one, by comparing the J cap components, and we have del Z of Hx minus del X of Hz, and in the right hand side, from the right hand side, I have minus of I omega epsilon 0 Ey. And then the last equation, that is comparing the K cap components from both the sides, I have del X of Hy minus del Y of Hx, and that equals to minus I omega epsilon 0 then Ez. So these are the three components we have from equation number 5, right? Now using the solution as I have taken in equation number 8. So equation number 8 I have just wiped out. It was the solution we are assumed that the form of H or the form of E, and then we have del Y of Hz. Del Y of Hz. We have the value of H as Hxyzt equals to H0 e to the power I kz minus omega t. So this was the form of H. Now as I find out the value of del Y of Hz, del Y of Hz. So it will be del Y of Hoz as the function in the right hand side, given as it is a function of z and t, H0 e to the power I kz minus of omega t. So we can't find out the value of del Y from the right hand side, and it will be, so this equation can be written as del Y of Hoz, and now then del Z of Hy. Now we have the value del Z, and it will be Ik. We have Ik and then H, so it will be minus of Ik then Hoy. Now in the right hand side it will be minus I omega epsilon 0, and then Ex is written as E0x. So let it be equation number 9. So this is the first equation. Now moving towards the second one. Now again here we have to find out the value of del Z, as the del Z value will be again Ik. So from the second equation we can write Ik, and then del Z of Hx means Hox, then minus, now del X of Hz, we can't find the value of del X of Hz, so we have del X of Hoz, and in the right hand side minus I omega epsilon 0 then Eoy, and it is equation number 10. I think up to this you have no problem. And then from the third equation we can write del X of Hy means del X of Hoy minus of del Y of Hx, that is del Y of Hox, and then in the right hand side minus I omega epsilon 0 Eoz, and let it be equation number 11. So these are the three equations. Now these three equations I have found taking the component form of equation number 5. Now if I take the component form of equation number 6, that is, we can find out these similar type of equations but for the electric field. So, similarly, proceeding from equation number 6, we just go on writing these equations. You need not to derive these equations for the electric field also. So you can write the values as del y. Here we have del y of HOZ. Similar equations are formed, or similar equations can be found by using the electric field. So you can write as del y of EOZ, then minus of IK. Here it was HOY. For the electric field it will be EOY. And then just remember that in equation number 6, in the right hand side we have positive I omega mu 0 H. So here only the negative sign will not be there for the electric field, and it will be I omega and not epsilon 0 but mu 0, then HOX. So just remember this thing. So this is equation number 12. Then moving towards the second equation, and from equation 10, in equation 10 we have IKHOX. So similar equation will be there, IKEOX minus of del X of EOZ, right? And then again in the right hand side we have I omega mu 0 and then HOY, and it will be equation number 13. So the last equation will be del X of EOY minus of del Y of EOX, and then in the right hand side I omega mu 0 then HOZ. It will be equation number 14. So these three equations can easily be written from equation number 9, 10 and 11, and you need not to derive this equation number 12, 13 and 14. You can write it just by writing that similarly from equation 6 we can have, and then you can write these three equations. Just remember that similar forms will be there for the left hand side of these equations, but in the right hand side, as in equation 6 we have a positive value, that is plus I omega mu 0 H. So for the right hand side we have to write it positive value I omega mu 0, and then following the values, following the equations for equation 9, 10 and 11 we have H0x, H0y and H0z, and thus we can find these three equations without bothering anything. So these are equation number 12, 13 and 14. Is it okay? Any doubts? If you have any doubts, mention or just give a thumbs up. Is it okay? Okay. Okay, fine. So now from this 6 equations 9, 10, 11, 12, 13, 14. Now we are going to eliminate we are going to eliminate the value of E0y. Now we are going to eliminate the value of E0y from equation number 10 and equation number 12 as well. So I am going to show you one of the equations, and then again we can write it as similarly we can found. So just eliminating the value of E0y from equation number 10 and equation number 12. So we can substitute the value of EOY. We can substitute the value of EOY from equation number 10. That is, EOY means this entire value divided by minus of, so from equation 10 we have the value of EOY, or rather EOY equals to minus, that is 1 by I omega epsilon 0, and then by multiplying it with the negative sign, it will be del x of HOZ minus of IK HOX. So this will be the value of EOY. Right. Now this value of EOY, I am going to substitute it in equation number 12. Okay, so it will be del y of EOZ minus IK, then EOY, that is 1 by I omega epsilon 0 del x of HOZ minus of IK HOX, then in the right hand side I omega mu 0 HOX. So we can omit these i's, and we have to find out the value of HOX. We have to find out the value of HOX. So del y of EOZ minus K by omega epsilon 0 del x of HOZ minus plus, and then again I K by omega epsilon 0 HOX, and in the right hand side I omega mu 0 HOX. Now I am going to omit these two equations, that is equation number 9 and 10. So taking or going to find out the value of HOX. So take HOX common. We have IK omega epsilon 0 minus I omega mu 0, and then putting K omega epsilon 0 del HOZ del x, and then minus of del EOZ del y. So I am just distributing these terms from the left hand side to the right hand side of this equation, and now we have so just simplifying this, that is HOX, and then IK minus of I omega square epsilon 0 mu 0 by omega epsilon 0. Okay. So now again epsilon 0 mu 0 means 1 by c square. So here I can write it as IK minus I omega square by c square, and then we have this omega epsilon 0, I can give this omega epsilon 0, I can shift this omega epsilon 0 in the right hand side. So it will be k by omega epsilon 0 del x of h o z. Just follow me, minus del y of e o z. So now, omitting from the top of this, so it will be HOX, and then take this I outside the equation, I by omega epsilon 0, it will be k minus omega square by c square, okay, and then in the right hand side k by omega epsilon 0 del HOZ by del x minus del EOZ del y, right. Okay, so HOX, and then I am putting this I in the denominator side, and that will be 1 by I. So 1 by I means minus of I. So it will be minus of I, and then omega epsilon 0. I am multiplying this with omega epsilon 0, and it will be omega epsilon 0 cancels with the first term, and then it will be k del x of HOZ, and then minus omega epsilon 0 into del y of EOZ. Is it okay? Now just multiplying this with the value minus, so we have I, and then omega, okay, now keep it here as it is, and then I think I have made a mistake here, k omega epsilon 0, and then here it will be k square, right? So HOX with a k square term, HOX with a k square term. Just get it there, that is, it is just a k square term, right? So it will be, so if I take a negative sign out of this, it will be HOX, then omega square by c square minus of k square, and then I can omit this minus from the right hand side, and it will be IK del x of HOZ minus of omega epsilon 0 del y of EOZ. Is it okay? I think everything is okay. Now, so the value of HOX, now this omega square by c square minus k square, this particular value, it can be, yes Urpita, you have pointed out rightly, so I have made the correction here. So now omega square by c square minus k square can be written as h square. So h square is again a constant value. So putting omega square by c square minus of k square equals to h square, we have HOX into h square. So HOX equals to I by h square, and then it is k del x of HOZ minus of omega epsilon 0 del del y of EOZ. So this is the procedure to find out the values of these components. That is, I have found out the value of HOX and it will be equation number 15. So as you can see that if you are going to derive these values, that is HOX, then HOY, EOX and EOY, that is the four components, you have to give a lots of amount of time. So just don't bother to derive these four independent values, and you have to memorize, just derive one of these values as I have shown here, how to find out the value of HOX, and then after finding one of these values, that is after finding the value of HOX, just write the other three values, that is HOY and then EOX and EOY as. So just write these other three values, and for this you have to remember these values, and it may be a tough job for you to remember these values, but it is easier to remember these values instead of deriving these another three values. So similarly, considering the other equations appropriately also, we may have the value of HOY, and it will be I by H square K del del Y of HOZ plus omega epsilon 0 del del X of EOZ. So it is equation number 16. Then EOX, the value of EOX can be written as I by H square K del del X of EOZ plus omega mu 0 del del Y of HOZ. It can be written as equation number 17, and then EOY, that equals to again I by H square, then K del del Y of EOZ minus omega mu 0 del del X of HOZ. So this is equation number 18. So I know that these equations can not be remembered so easily, but if you have to derive these values, you have to spend a lot amount of time, and this amount of time is not given to you. So you have to remember these three equations, the values of HOY, then EOX and EOY. Is it okay till? Again, just give a thumbs up, or you have any queries. Ask me. Now, after deriving these four equations, now what are these equations tell us? They actually gives the values, they actually give the values of HOX, HOY, EOX, EOY. What are these? These are the transverse components. These are the transverse components, and they are being completely determined by the longitudinal components. As you can see from these four equations, in every equation in the right hand side, we have the longitudinal components, that is HOZ or EOZ. So HOZ and EOZ are only present for each of the right hand side of each of these equations. So the problem of determining magnetic field or electric field inside the waveguide actually reduces to that of determining the longitudinal field components only. So if we have the longitudinal field components, that is HOZ or EOZ, we have to find out both the values of the longitudinal components, that is EOZ and HOZ. And if we have these values of EOZ and HOZ, we can easily find out the transverse components, that is HOX, HOY, as well as EOX, EOY, as because these transverse components can be found out by only determining the longitudinal components of the electric and the magnetic field inside the waveguide. So we have to consider two separate conditions. Now we have to consider two separate conditions. Case 1. Just be careful. Now, for case 1, we are considering that if EOZ equals to 0, what will happen? If EOZ equals to 0, then entire field, as because only two components are present, one for the electric field and the other for the magnetic field. So now if one of these, that is if EOZ equals to 0, then the components or the field is only determined by the component HOZ. I am again repeating this, that if EOZ equals to 0, then from these four equations, that is going from 15 to 18, in the right hand side, if EOZ equals to 0, then we have only the term HOZ present. Then only the term HOZ present for each of these four equations. So only the magnetic field or the H field is so the entire field can be determined by the component HOZ. And for this particular reason, these waves are called H waves. So for any wave, if the component EOZ vanishes, or if EOZ equals to 0, then the entire field will be determined by the component HOZ only. And since this is known as, or these type of waves are then known as H waves. So if EOZ equals to 0, the field is determined by HOZ only, and these waves are known as H waves. So these are the H waves, and here you can see that only transverse electric field exists. Transverse electric field exists, and the corresponding wave is also called transverse electric or TE waves. As you can see, that if the value of EOZ equals to 0, what is EOZ? EOZ is the longitudinal component. EOZ is the longitudinal component of electric field. EOX and EOY are the transverse components of the electric field. And now since EOZ is 0, that means the longitudinal component is 0. That means only these values EOX and EOY are present, but EOZ is already equals to 0. That means only transverse electric fields are present, not the longitudinal component is present here, and so these waves are also known as transverse electric field. So transverse electric field means the longitudinal component of electric field is absent. Transverse electric field means the longitudinal components of the electric field is absent. That means EOZ is 0. EOZ is 0, and then only the transverse components are present, and then this type of waves are known as transverse electric or TE waves. So H waves, TE waves are all the same. H waves or TE waves are the same type of waves. So this is the case 1. Now let's move on to case 2. The other can be that if now HOZ is 0. If HOZ equals to 0, again considering equation from equations 15 to 18, these 4 equations, and you can again similar by following the similar arguments, you can tell that if HOZ equals to 0, here HOZ, here HOZ, HOZ and HOZ. So if HOZ is 0, then the entire field is determined only by the EOZ component. The entire field is will be determined by the component EOZ. Right? So now following the similar arguments, we can represent or we can call this type of waves as E waves, electric waves. We can tell this type of waves, we can name this type of waves as E waves. And again, as the transverse component, as the longitudinal component, that is HOZ is 0, that means only the transverse magnetic components, that is HOX and HOY. HOX and HOY are present. So because the transverse magnetic fields are present here, longitudinal component, that is HOZ is vanishes. So we can call this type of waves as E waves as well as the transverse magnetic waves or TM waves. So these are the TE waves and TM waves. Right? Now, the third case can also be there. That is, both the components, both the longitudinal components, that is EOZ as well as HOZ are 0. So, case number 3. Case number 3 will be if both EOZ as well as HOZ are 0. What will happen? So if both the components, from the theoretical aspect, if both the longitudinal components of electric field and magnetic field vanishes, then from the similar arguments we can tell that only the transverse components of electric and magnetic fields will be there. If the longitudinal components of electric field and magnetic field both vanishes, then only the transverse components of electric and magnetic field will be there. So then this type of waves can be called as transverse electromagnetic waves. So these can be known as the transverse electromagnetic waves or TEM waves. So if the components of EOZ as well as the component of HOZ, both of them are equals to 0, then from theoretical aspect we can call it that the transverse electric and magnetic waves, because the longitudinal components, that is HOZ and EOZ, are vanishes. So only this type of waves can be termed as the transverse electromagnetic waves. But again, from the values of equation number 15 to equation number 18, if we ponder, we can find that if HOZ and EOZ, if HOZ and EOZ vanishes or they are equals to 0, then these transverse components, that is HOX, HOY, EOX, EOY, both, all the values, all these transverse components EOX, EOY, HOX, HOY are equals to 0. So from equation 15 to equation 18, we can show that in this case, the entire field inside the waveguide vanishes identically. Vanishes. Now this indicates, what does it implicate? It implicates that pure transverse electromagnetic waves cannot exist in a rectangular waveguide. So in a rectangular waveguide, pure transverse electromagnetic waves cannot be propagated or cannot be existed. Okay? So cannot exist pure transverse electromagnetic waves in a rectangular waveguide. So we have to concentrate among the transverse electric as well as the transverse magnetic wave inside a rectangular waveguide. Okay? Any problem? So if you have no doubts till this, I will continue for the TE waves. For the TE waves, and now as we have shown that for the TE waves, the component, as this is the transverse electric waves, so the component, that is the longitudinal component of electric field, is 0 here. That means for TE waves EOZ equals to 0, as I have already discussed. And now as EOZ equals to 0, that means the entire field will be determined by the component of HOZ only. So the wave equation satisfied by H, I have already derived that. So now I am going to discuss about the TE waves or TE modes. So the wave equation will be delta square plus omega square by c square into capital of H equals to 0. And now as the Z dependence of H is assumed to be of the form of e to the power I k z. So the above equation, we can write it as by the component, and if H can be written as H0 e to the power I k z, if the Z component can be written as this. So by expanding this, we can have delta square means del 2 del x2 plus del 2 del y2 and then del 2 del z2. So del z of H, we have I k then H, and if we find del 2 del z2 of H, then it will be I square, that is minus of k square into capital H. So we can write del 2 del x2 plus del 2 del y2 plus omega square by c square and then minus of k square and then HOZ equals to 0. So I have taken the scalar component, scalar part, and again, as I have already shown that omega square by c square minus k square can be written as small h square. So this equation can be written as del 2 del x2 plus del 2 del y2 plus h square into capital HOZ equals to 0, and let it be equation number 19, right? Now we have to go out, find the value of HOZ. As because by finding the value of HOZ, or if we can find out the value of HOZ, then all the four transverse components, that is EOX, EOY, HOX and HOY, can be found out by putting the values of HOZ there in equation number 15 to equation number 18. Now for the solution of equation number 19, we assume a solution of the form, HOZ, which is actually a function of x and y. So we assume let HOZ, which is a function of x and y, can be written as some function of x and some function of y, the product of f1x and f2y. So this is the procedure, as you know that this is the procedure for the separation of variable method. So I am going to use the separation of variable method here. So now just find out the value of del 2 del x2 of HOZ. What will be the value of del 2 del x2 of HOZ? So keeping f2 constant, that is, or f2y constant, we have it will be d2 f1 then dx2, and then the value of del 2 del y2 of HOZ, it will be f1 keeping the constant f1, and it will be d2 f2 dy2. So just putting these values in equation number 19, we have del 2 del x2 HOZ, that means f2 d2 f1 dx2 plus del 2 del y2 HOZ, that means f1 into d2 f2 dy2, then plus h square HOZ, or we can write it as equals to minus of h square. HOZ means f1 into f2. I am omitting, just I am not going to write time and again the functional form, that is f1x, f2y. So just writing f1 and f2. Now again, from the method of separation of variables, now we have to divide this entire equation by the product of f1 and f2. You know already. So by dividing this entire equation by the product of f1 and f2, we have 1 by f1 d2 f1 dx2 plus 1 by f2 d2 f2 dy2, and that equals to minus of h square. So just it is a constant, and we can write this constant as minus of h square, that is kx square plus ky square. So I have written h square equals to kx square plus ky square. Okay. So we have the variables are separated, and the equations will be 1 by f1 d2 f1 dx2. So the separated equations are 1 by f1 d2 f1 dx2 equals to minus of kx square, and 1 by f2 d2 f2 dy2 equals to minus of ky square. Now these two equations are very much known to us, and we have the solutions write from their form. That is, we can write F1. We can write F1 equals to A cos kxx plus B sin kxx, and then F2 can be written as C cos kyy plus D sin kyy. So F1 and F2 can be written as F1 and F2. So the solutions of F1 and F2 can be written as F1 equals to A cos kxx plus B sin kxx, and then F2 can be written as C cos kyy plus D sin kyy. So these are the two equations, F1 and F2, and thus the solution, final solution of equation 19, it can be written as HOZ xy. So the final solution will be HOZ xy equals to just the product of F1 and F2, and by putting the values of F1 and F2 we have A cos kxx plus B sin kxx into C cos kyy plus D sin kyy. So this is the final solution. This is the final solution of equation number 19, and here it can be written as equation number 20. But remember, now we have four constants A, B, C and D, and these are the arbitrary constants. So we have to find out these values of the constants A, B, C and D by taking appropriate boundary conditions. And where from we have the boundary conditions? We have to consider a rectangular waveguide, as this entire derivation is based on the rectangular waveguide. So now we have to take a rectangular waveguide structure, and in the screenshot or in the image of this particular video, you can find a rectangular waveguide. A picture of rectangular waveguide is given, and I am considering this particular rectangular waveguide structure, and from this the dimensional values are also taken as A and B. So just drawing that particular picture. So this is the waveguide what I am talking about. So this is X and this is Y. Now so you can find this image on my video image as well. Now this is the length A and this is the value of B, and this is nothing but the Z axis. So the waves are propagating along the Z axis, and as the walls of the waveguide is made up of perfectly conducting walls they have, so the boundary conditions from this structure, from this rectangular waveguide, we can write the boundary conditions. The boundary conditions as at x equals to 0 and x equals to A. So at x equals to 0 and at x equals to A, Ey, that is the electric field along the y-axis, Ey equals to 0 at x equals to 0 and x equals to A. This is one pair of boundary conditions, as well as Ex will be 0 at y equals to 0 and y equals to b. So this is the another pair of boundary conditions. So we have 4 boundary conditions and we have also 4 constants to determine. So let's move to find out these values. Now as from equation 18, we have EOY equals to, from equation 18 you can see that EOY is actually proportional to the value of HOZ, that is del x of HOZ, as because in equation 18 you have the value of EOZ, but as because I am discussing only about the TE modes, that means EOZ is 0, and so from equation 18 we can write that EOY is actually proportional to del x of HOZ. And now as del x of HOZ and EOY, so the value of EY, we have the value of EY equals to 0 at x equals to 0. So that means this value will be 0 at x equals to 0. Is it not? As the boundary condition tells us that the electric field along the y-axis will be 0 at x equals to 0. So from equation 18 we have the value of EOY, which is nothing but proportional to del x of HOZ, and it will be 0 at x equals to 0 following this first boundary condition. Okay. So let's apply this boundary condition into equation number 20. So we have to find out the value of del x of HOZ. So del x of HOZ, we have del x of HOZ, that means cos term, it is minus kx a sin kxx plus kx into b cos kxx, and only these two terms, that is c cos kyy plus d sin kyy, will be there. So we can write this kx outside and it will be this. Now this particular value del x of HOZ equals to 0 at x equals to 0. So just by putting the value of x equals to 0, we have kx and then minus a sin kx 0. That means 0. Only we are left with b, kx b into c cos kyy plus d sin kyy equals to 0. And now you can tell that as kx cannot be equals to 0, c cos kyy plus d sin kyy, if this term vanishes, then equation 20 also vanishes. So we can conclude that only the value of b from this particular equation, we can conclude that yes, the value of b should be 0 from this condition. Therefore, equation 20 gives, after putting the boundary condition, b equals to 0. Right? Any doubts? Have you any doubts? If not, give a thumbs up. Okay. So now one constant b vanishes. Now let's move on to equation 20 gets reduced. Now let's move on to equation number 17. Just by considering equation 17, we have that EOX. So let's remove this, remembering that the value of B vanishes. So now considering equation number 17, and you will find that from equation 17 we can conclude that the value of EOX, from equation 17 we can find out the value of EOX, and it is actually proportional to del del y of HOZ, again by similar arguments. Now as because by del del y of HOZ, and this x component is actually vanishes at y equals to 0. So that means the component del del y of HOZ will be 0 at y equals to 0. So let's find out the value of del del y of HOZ. Remember, B is not here. So we have A cos kxx, and then it will be taking ky outside. I'm writing the positive value first, that is d cos ky y minus c sin ky y, right? So now the value of this is 0 at y equals to 0. So if we put the value of y equals to 0 here, we have this term vanishes. We will left with only the value of d. So at y equals to 0, we have ky a cos kxx into d that equals to 0, right? Now if the value of a is considered at if the value of a, sir b sin hobe na, where b sin, where from b sin, I don't get it. Kaushik, I don't get it. B sin, where from you find b sin? I have written b sin. So if the value of a here taken as 0, already b is 0. So if a also taken as 0, that means equation 20 again vanishes. So we can't have the value, we can't take the value of a as 0. So we are only left with d equals to 0. So we are only left with the value of d that equals to 0. From this particular equation, we conclude that d must be 0. Okay? So equation number 20 now again reduces. We have the value of b, we have the value of d, both of them vanishes. So the value will be HOZ, that is equation number 20 can be written as HOZXY equals to A cos kxx into C cos kyy, as because both the terms b and d, both the constants b and d already vanishes. So the entire value, now as these two constants are also left here, that is a and c, we can combine these two constants and we can write it as H0. It can be written as H0, then cos kxx into cos kyy, and this can be written as equation number 21. So this is actually the reduced form of equation 20, but we have two boundary conditions left with us at x equals to a and at y equals to b. Now again considering the equation number 18, that is EOY. Now considering, so let's remove equation number 20 as because it has been reduced, and So this is the form of solution or the reduced form what we have. Now again considering the condition number 18, that is again the value of EOY. We have EOY, that is equation number 18 tells us that EOY is proportional to del x of HOZ, and now it is also 0, EY 0 at x equals to A. So we have the boundary condition left with us at x equals to A. So now del x of HOZ, del x of HOZ, it will be H0 kx cos kyy into minus of sin kxx. So after differentiating equation number 21 with respect to del x, with respect to x, we have H0 cos kxx means kx sin kxx, and cos kyy will be there. So this value is 0 at x equals to A. So just put the value of x equals to A. We have minus H0 kx sin kxa into cos ky y equals to 0. Right? Now as you can find that if the value of cos kyy equals to 0, cos kyy equals to 0, what will happen to equation number 21? Equation 21 will be 0. So you can't have the value of cos kyy equals to 0, you can't have the value of h0 equals to 0, as again by taking h0 equals to 0, equation number 21 will not be there. So we have left with only that term sin kxa can be 0, as sin kxa is not in equation number 21. Okay, so we have therefore sin kxa equals to 0, and as we know from the general solutions of trigonometry, we have sin theta equals to 0 when theta equals to n pi. So I have taken equals to m pi, where m is an integer, 0, 1, 2, etc. So the value of kx can be given as m pi by a. So we have the value of kx and it is m pi by a. Now again considering equation number 17, we can write that equation number 17 we can write that EOX is proportional to del y of HOZ, and that actually equals to 0 at y equals to b. So this is our last boundary condition. At y equals to b, Ex equals to 0. So putting this value, we have del y of HOZ. So now we have to find out the value of del y of HOZ, and we have H0 ky, then minus of sin kyy into cos kxx, and then putting at y equals to b, we have H0 minus ky sin kyb into cos kxx equals to 0. Again by similar argument, we can't have H0 equals to 0, we can't have cos kxx equals to 0, as for both these two values equation number 21 vanishes. So we are only left with the value sin kyb equals to 0. So therefore sin kyb equals to 0, and again we can take this value equals to sin n pi. Therefore ky can have the value of n pi by b. So we have these two values. Find out kx and ky just by putting these two values of kx and ky in equation number 21, we have HOZ XY equals to H0 cos m pi x by A into cos n pi y by B. Right? So this is the solution of equation number 20. You can find that here the components HOZ, that is the transverse component. Sorry, this is the longitudinal component. It is the value depends on M, N and A, B. M, N and A, B. Now these values M and N are the modes of propagation. These are the modes of propagation, and A and B are, as you know, these are the dimensions. These are the dimensions of the rectangular waveguide. So putting the different values of M and N, we can have different values of HOZ, and if we have the values of HOZ, then the other transverse components, that means EOX, EOY, HOX and HOY, all can be found. Now, as the value of M equals to 0, N equals to 0, we have cos 0 means 1. So, HOZ XY equals to, for M equals to 0, if you have to find out the different transverse electric field, that is TE. Now let's find out another one thing, another important aspect, as we have the values of Kx and Ky here. So just as we have taken when we have solved the equation, we have taken the value of a constant h square. You can remember that h square is written as kx square plus ky square, and now we have the values of kx and ky, as we have taken h square equals to kx square plus ky square. Now what is h square? H square was omega square by c square minus of k square, and kx means m pi by a square plus n pi by b square. Okay, so k square, the value of k square will be omega square by c square minus m pi by a square plus n pi by b square. So this will be the value of k square. Let it be equation number 23. Now one physical aspect can be drawn from this. Now you can see that the value of omega square by c square can be less than the value of this m pi by a square plus n pi by b square. It can happen. It can happen. Now if the value of omega square by c square is less than the value written inside the third bracket, what will happen? We have the value of k square. Then we have the value of k square is a negative value. We have the value of a k square is negative, and if k square is negative, then it implies that k is an imaginary quantity. That k will be an imaginary quantity. Now what is k? K is nothing but the wave number or the propagation constant. Now if for any certain wave the propagation constant or the wave number vanishes, that means the wave is not going to propagate through the waveguide. The wave is not going to propagate through the waveguide. It actually gets attenuated. It actually gets attenuated. So for the value of omega square by c square less than this particular value, you will not get any wave propagating through the waveguide. Now another thing can appear, that the value of omega square by c square, is greater than, when the value is greater than m pi by a square plus n pi by b square, again you can say that if this value is greater than this, then k square is a real number. K is a real number. K square is positive, so k is real. It means k is real. So that means the wave certainly propagates. This wave certainly propagates through the waveguide. You have no attenuation whatsoever for this particular case. Now here, after considering these two values, you all can conclude that there must be a certain value of frequency. There must be a certain value of omega, what we called it as the cutoff frequency omega c. And below the particular value of this cutoff frequency, no wave can propagate through the waveguide. So the cutoff frequency or the value of the cutoff frequency should be omega c, and that equals to omega c, that equals to c into square root of m pi by a the square plus n pi by b square. Right. So this is the value of the cutoff frequency below which no wave will be there. No wave can propagate through a waveguide. So you have to maintain this particular cutoff frequency value. Right. Now as you can see that if we have the value of the frequency, we can write the cutoff wavelength as well. So the cutoff wavelength, that is lambda c, it can be written as omega c, c by lambda means c by omega by 2 pi, and the value will be 2 divided by m by a square plus n by b square. So this is the value. Let it be equation number omega c is equation number 24, and the value of lambda c is equation number 25. So the cutoff wavelength, the value of the cutoff wavelength, I know I have crossed 1 hour 30 minutes, but just a few minutes more. The value of cutoff wavelength can be written as lambda c just by c by f frequency, and as omega c is the angular frequency, so it is c by omega c by 2 pi, and we have lambda c equals to the value of this, that is 2 by square root of m by a square plus n by b square. And again, propagation is possible only when the wavelength lambda is less than lambda c. The wavelength lambda is less than the value lambda c, as because frequency, for the frequency part we have to say we have already concluded that omega must be greater than omega c, but as the frequency and the wavelength are inverse to each other, so whenever we are talking about the wavelength, we have to tell that lambda must be less than lambda c to make a wave propagate through the medium or through the waveguide. Now as you can see that the value of this cutoff wavelength lambda c is entirely depends on the transverse dimension of the waveguide, that is a and b, and also on the modes of propagation, that is m and n. Now let us consider the value of m equals to 0 and n equals to 0. Let us consider the value m equals to 0 and n equals to 0. So this is the 0, 0 mode. This will be the 0, 0 mode for m equals to 0 and n equals to 0. If you put the values of m equals to 0 and n equals to 0, you have a value of infinity for the lambda c. So that means that the transverse electric mode, that is transfer a T wave 0, 0 mode, is not possible. TE00 is not possible, as because for m equals to n equals to 0, for m equals to n equals to 0, all the field components vanish, right? Okay, now let's put the value m equals to 0 and n equals to 1. Put the value m equals to 0 and n equals to 1. What we have for m equals to 0 and n equals to 1? If we put the value of m equals to 0 and n equals to 1, we have lambda c equals to square root of n by b square, or it will be twice b. N equals to 1, so it will be lambda c 0 1. So for lambda c 0 1, that is the transverse, for transverse electric waves, the mode m equals to 0, n equals to 1 is possible, as we can find that the value of lambda c 0 1. So this is TE01. That means lambda c 0 1 is equals to twice b. So it is possible. Now let's find out the value TE10, and then by putting m equals to 1 and n equals to 0, we have twice a. So it is also possible. So for the transverse electric field, TE00 is not possible, but TE01, TE10, both of them are possible. Now for these particular two values, for any regular rectangular waveguide, we have the value of A is greater than the value of B. We have the value of A greater than the value of B. That means the value 2A is greater than the value 2B, and then this lambda c, or this TE10 is the dominant mode. It is known as the dominant mode. Okay, so which mode has the higher value, that is the larger dimension, that mode is regarded as the dominant mode. And here for a rectangular waveguide, generally the value of A is greater than the value of B, and as a result this TE10 mode is the dominant mode of propagation. So this is the entire theoretical discussion, mathematical derivation of the transverse electric waves. So thank you.